All right, and so you're going to fill in with these questions here. And basically the reason I'm doing this is because I'm going to post a different version with different problems on Canvas afterwards. All right, so again, just so you can see it kind of in paper format here. So what you want to do is start filling in with the molecules that I've drawn up there. All right, and so again, what I'll post on Canvas will be the same thing, but just with some different problems as well. All right, so I'll kind of zoom in so everybody can see what's up here.
Do you want us to name them?
These are nomenclature problems, yep. So for right now, let's just fill in our worksheet, go in and draw all these structures. We'll fill in all these pages and then leave you guys to it. All right, I'll scroll down a little bit. For these ones, I'm giving you the name, right? And you're going to draw me the structure. Come grab one of these. We're sort of going to fill in the problems that are on the board here. And I'll go back once we're done and let you copy. All right, so these are all nomenclature. When I give you the structure, you give me the name. When I give you the name, you give me the structure. Okay? If we go over to the next one, these are these conformation of cyclohexanes. And so this is this template that I told you that we're going to be filling in, right? So you have these three problems here. There are these three cyclohexane, substituted cyclohexanes here above each kind of equilibrium sign here. You're going to use that and then follow the instructions. So you're going to fill in your little diagram within this first example, those two methyl groups. Where should they go based on that little diagram that I gave you? Identify which one is the more stable conformation and what are the positions of the substituents in that more stable conformation. Okay, so copy down those three cyclohexane derivatives up there. So like these molecules up here, that's what you're copying down. Yep, so you can, the instructions are on there, but yes, you're gonna sort of put these, just like I was doing in the lectures, right? You're gonna copy these methyl groups. Where do they go on this chair conformation? Show it on both sides of the flip. Identify which of those conformations is the more stable one. Okay, so we got these three molecules here. All right, and you'll notice that I also gave you an additional set on the very, very back. This is for you to practice with at home. Okay, because again, I'll post this same sort of thing, but with some new problems on Canvas, and so this is what you can use to fill that out when you're doing your practice problems at home.
I think that's what I'm drawing right now.
Perfect, that's what today's for, to ask questions about all this jazz. All right, and so then the last page, first of all, you're going to, I'll go back here in a second. All right, first of all, you're going to write the balanced chemical equation for the combustion of hexane. Okay. And then copy down these molecules here. These are these radical halogenation reactions here. And I'll put those values for the reactivity of primary, secondary, and tertiary positions up on the board. I don't remember what it is for bromine. Bromine is off my head, but. Two, maybe? I'll have to look this up. All right, remember we need these reactivity factors to figure out what the the major product is in these reactions. I gotta look it up for bromine, but we'll need those values. So for right now, just making sure you're copying down those molecules. Honestly, start in the place where you're least comfortable. If you're good at nomenclature, don't bother with nomenclature, right? It's all about sort of getting feedback on the places that we're stuck. So start in the area where you feel like you're the least confident. All right, at some point I'll sort of go through and fill in answers. If I'm getting a lot of the same questions, I'll stop and go over that one explicitly. But this is all about just seeing sort of on paper what my expectations are going to be come exam time. All right, I will go back to this page. I know that was requested, seeing these three molecules again. And let me look up that reactivity of bromine. All right, we all good here? I think there are also some people that want to see that nomenclature page again, so we're all good on this one? Cool, all right, so this is that first page again, those nomenclature problems. All right, you can also check your work with your neighbor. I mean, I know it's 8 a.m. I would hate me too if somebody was trying to talk to me for an hour straight at 8 a.m., right? But it's of course what we all signed up for, so that's what we gotta do. But yeah, that's the whole purpose of today, is let's get comfortable with these types of problems from chapter 2. Who didn't get their quiz back last time? I don't have it if you took it in the testing center yet. I do have it, but I don't have it graded yet and entered. But who took it in class that hasn't gotten it back yet? All right. Come on up. Let me get your last name. I'll be able to find it that way. Say it again?
Jenkins.
G-H-I-J.
Thank you.
Say it again? Yeah, there you go.
Gil.
What is it? One more time? What does it start with? What's your last name start with? Okay, sorry. Gotcha.
Beach.
One more time? Oh, yeah, sorry. Where in this pile would that be? Here we go. Oops, sorry. So just start filling in those problems and then I'll scroll to the next page for you. So it kind of doesn't matter in terms of like, obviously with nomenclature, the numbering is really important, right? But for here, the numbering is just going to help you find what carbon goes to what.
This one because they're saying molecule, but this one is going to be molecule.
Right, so it wouldn't matter if you made this one 1 and then this one 3, or this one 1 and this one 3, as long as they were spaced out like that.
Okay.
So if you say, and you just, make it simple, this was 1, 2, 3, then you're going to map this methyl group on the carbon 1, and this isopropyl group on the carbon 3.
Okay. All right. Thank you.
Cool. All right, let me show you the next page real quick. In the corner here. So this will be for that second page. These 3 molecules are what you want to copy down. Did you just get here?
Yeah.
All right, so what you want to do is copy these problems down here. I'll flip it to the first page here in a second, but you can copy down these 3 structures here. All right, so this is kind of like the blank shell of a quiz, and you're going to fill in these problems. No, so the wedges still stay a wedge from one side to the other. The other thing is, you want to actually put in which position the methyl group is in, right? Because you got these two bonds here. This is as if there are two methyl groups off of this carbon. Only one of those positions actually has that methyl group, and as you've drawn it, it's that wedge, right? So you want to put like a CH3 there to indicate there's nothing at that position. Because that's how you can tell which one's going to be more stable, right? Where with regard to these structures here, do big groups like to be in the axial position or the equatorial position? The equatorial position. That's the whole logic as to which conformation is more stable than the other one. The one that has the biggest group in the equatorial position. So let's go through and do one of these together real quick, because I know that this one's kind of a weird one for people. So, step A says draw the substituents on the chair flip diagram provided. What the hell does that mean? These methyl groups are the substituents. Right? So I'm going to fill in on my diagram which bond has those methyl groups on it. There's a good question about like how do I number these things and everything like that. When we're numbering for nomenclature, there's this whole logic behind it. When we're numbering just to figure out what carbon's what, it really doesn't matter which one you start with as long as you get your spacing correct. So I could say that this one's 1 and this one's 2. It could also be the other way around and I would still arrive at that same answer. Okay, that's not the case for nomenclature, but in terms of just placing, mapping what carbon is what, you can sort of arbitrarily start numbering, counterclockwise, clockwise, it really doesn't matter. Okay, so I'm going to put a methyl group on carbon 1 and a methyl group on carbon 2. I'm going to have to make sure to put in carbon 1, that methyl group's on the up position, right? It's pointed out at you. So that means it should go specifically on this bond here. Right, at each carbon, I'm going to look, this is my carbon 1. There's always going to be a bond on top and a bond on the bottom. The wedge means I need to put it on the top bond. The dash means I need to put it on the bottom bond. It is not as straightforward as to say the wedge is always axial and the dash is always equatorial. That's not how it works. Right, because if we move on to carbon 2 here, again, we have one bond on the top and one bond on the bottom. Notice on carbon 1, that top bond is in the axial position. But on carbon 2, that top bond is in the equatorial position. Okay? So now I'm going to have to put my methyl group on carbon 2. Should I be putting it on the top bond or the bottom bond? Who thinks the top bond? Who thinks the bottom bond? Right, so it's at a wedge, or it's not at a wedge, it's at a dash, which means it's pointed into the page, pointed away from you. So this other methyl group would be located here. Right, so that's how I would start this problem, is I'm going to map what I see, these substituents, these two methyl groups, onto my actual chair flip diagram. All right, now the chair is going to do its flip. So axials are going to become equatorials. Equatorials are going to become axials. Again, I just need to follow along what carbon's what. I'm going to put my methyl groups on carbon 1 and 2 again. But again, on the other side of my chair flip, what was once the axial position is actually the equatorial position now. So that's where I would put my methyl group. And same thing over here on the carbon 2, what was once the axial position is now the equatorial position. So I would put my methyl group there. All right, so I'm mapping the substituents onto this chair flip diagram. From here, I can determine which one, so then the next step is determine which one is the more stable conformation. Looking at these two, which one's going to be the more stable conformation, the one on the left or the one on the right? Who thinks the one on the left? Who thinks the one on the right? Right, we want those substituents in the equatorial position, so this one is more stable. So then lastly it says identify whether your substituents are in the axial or the equatorial position in the most stable conformation. In this case, both of them are in the equatorial position. All right, so equatorial, equatorial.
So they're the substituents are more fungible in it.
Correct. Yep. In this case, both of them are in the equatorial position. The whole logic, if one of them was axial, one of them was equatorial, you would go for whichever one is bigger wants to be in the equatorial position. Right? Large groups do not like the axial position. All right, so that's how we do this type of problem here. So everybody can take a second and work on that second one in the series. Here you're going to play the same game, right? Step one, map them onto that chair flip diagram. In this case now we have this methyl substituent, but this one's this big bulky, what would be called like an isopropyl, but we don't really need to worry about the name of it. Big bulky substituent here, right? Here's a carbon here, and it's got two methyl groups sticking off of it. Okay, so this is now a big bulky substituent. So you want to map those two onto our chair flip diagram. Did you get a worksheet? Copy these structures down we're on the second page here. I'll flip it to the first page here in a second, but first page is a little more straightforward. It's just nomenclature. All right, so I'm going to kind of quietly fill in answers here so you guys can just check your work. But again, if you don't understand, make sure you flag me down and like have a conversation about it, right? That's the whole purpose of today, is to practice and get some sort of feedback on what we're doing right and what we're doing wrong. I know people don't like looking like they don't know what they're doing in front of the instructor. You don't have to worry about looking stupid today. You got to worry about looking stupid on the exam, right? So this is the whole point. Let's flush this all out now. bonds on the bottom would be the gases. So that's why I put the methyl group on the bottom bond here. I go to carbon 3, bond on top, bond on bottom. This is now a wedge, so that big group's going to go on the top bond here. And then again, following my carbons from one side to the other. If it used to be equatorial, it's going to become axial. And if it used to be axial, it's going to become equatorial. And notice that it stays top bottom, or top bond, bottom bond, top bond, bottom bond. It's still on the bottom, right? So this one, yeah. Yeah, that's good. Yeah, we'll do one of these together.
Okay, sounds
But
good.
yes, you're right. Absolutely. Go ahead. More highly substituted.
I didn't know about that one.
So this one you'll actually have two, because they're primary ones, right? But there are two different secondary ones here. So there would be two of those most stable ones. All right, yeah, let's do one of these radical halogenation ones real quick. Okay, so first of all, if you didn't take a second, you can take a second to copy these 4 molecules. Those are our questions here. Okay, so the first step is to draw the most stable alkyl radical intermediate. All right, so first of all, in these carbons, you're going to have a radical on, or in these questions, you're going to have a radical on one of your carbons in your molecule. Right, that's how these reactions take place here. There's this whole logic behind certain radicals are more stable than other radicals. What's that logic? Yes, exactly, right? So the more highly substituted the carbon is, the more stable the radical. So we can just make note real quick. Tertiary radicals are more stable than secondary radicals, are more stable than primary radicals. Right? So if carbon has 3 neighbors, that's going to be your most stable radical compared to if it only has 2 neighbors, compared to if it only has 1 neighbor. All right, these are the least stable. And note that when we draw our free radicals, that's just like this lone pair electron, but it's not paired, right? It's a single electron, a single dot on that carbon. Okay, so when we're going to our structures, let's actually do this second one, is a little bit easier. We're going to look at all the carbons in this molecule, and we're going to figure out which one is the most highly substituted. In this particular example, we have 3 primary carbons, right? Carbons that only have 1 neighbor. But then we have this middle carbon, which is a tertiary carbon. So our most stable radical will be putting the dot on that middle carbon. That's how I would draw the most stable intermediate for this reaction here, where I put that free radical on that most highly substituted carbon. Okay? So let's go to this first one here. You're going to go through and you're going to label each of those carbons as being either primary, secondary, or tertiary. All right, what are these terminal carbons? One on either end. Primary. So these are both primary. What about carbon 2? What about carbon 3? And then carbon 4 is also secondary. All right, so again, the radical, the most stable radical is going to form on the more highly substituted carbon. In this case, I actually have 2 because there are these equivalent positions. So So I have one where it forms on carbon 2,
It's not 3 because of the symmetry.
and then another one, exactly, I was just gonna get there. So then another one where it forms on carbon 3, and then why wouldn't I have to include this one here, where it forms on carbon 4?
Because it would be the same.
Yeah, because these two are equivalent. All right. That would be worth a heck of a lot of partial credit if you put 3 down instead of just the 2, but nonetheless, I want you guys to sort of get to seeing to how these two structures here are actually equivalent, right? If I just took this thing over, picked it up and flipped it like a pancake, I would get the other structure. All right, so in this case, I would have these 2 most stable intermediates. All right, so that's part A. Part B is I'm going to draw the major product of this reaction. So first of all, what are the products of these reactions? What would I do to draw the various products? These products are what we would call, well, so first of all, if we just look at the name, halogenation, right? So you're sticking a halogen on your molecule, okay? So if I were to draw all the possible products of, for example, this first one here, I would just take each carbon, right? So good idea how you're going to approach all these reactions. Start with what's given, right? Put down that pentane, that 5-carbon compound. There's not going to be any weird rearranging going on. You're not going to lose carbons. You're not going to gain carbons. So start with the shell of what's given here, that pentane, right? And then we can go through and stick chlorines on each one of those carbons. And again, because of symmetry, I would only have to draw those 3, right? If I put one on carbon 4, they'd be equivalent to the second structure I drew. If I put one on carbon 5, it'd be equivalent to the first structure that I drew. Right, again, because if I just took it up and flipped it, I get the same thing. What's up?
So the other chlorine is going to be HCl then, right?
Yes.
Another product?
Yeah, it is. Yep.
Every time, right?
What's up?
Every time?
Every time. And honestly, though, we only really care about the organic products.
Yeah.
This is where we get kind of lazy in organic chemistry versus general chemistry. General chemistry, we're always really good at having these balanced chemical equations. In organic chemistry, we really care what happens to that carbon-containing molecule. It's all about turning this compound into something else, turning your substrate into something else.
I'm confused about the chlorine on carbon 1.
We don't know what our major product. These are our 3 potential products.
Okay.
We got to do a little bit more work to figure out which one's actually the major product.
Okay, got it.
Okay? So first step 1 is to just like sort of draw all the different ones here. Okay? Because in these problems, it's not as straightforward as to say that it's always going to form on, for example, carbon 2. We got to do a little bit of math using our reactivity factors here. Okay? So I got to figure out which 3 of these products is going to be my major product. I'm actually going to move this over so I have a little bit more room. Okay, so we said that we had pentane, radical halogenation, and we have these 3 potential products here, right? And our goal is now to figure out which one is the actual major product. To do that, I have to use these reactivity factors, right? Because on the one hand, yes, the more stable radical is going to be on the more highly substituted carbon. But there's also like a little bit of a numbers game here, right? The carbons that have more hydrogens have more of a chance of being substituted just by the fact that they have more hydrogens. So we got to take these 2 things into consideration using these reactivity factors, okay? So what we're going to do is we're going to look at this here. And we got to ask ourselves, how many hydrogens could we have substituted that would lead me to this product here?
2.
So it's first of all, if we look at this carbon here, how many did it originally have? It would have had 3 on there. Okay, but it's not 3. Does anybody else see where those other hydrogens are that I could substitute? On the other side, exactly. So also, if I substituted any one of these 3, I would have that same product. right? Because of symmetry. So again, just think about it. I'm going to take this away, put it with the chlorine. That's that structure. If I take this hydrogen away, substitute it for a chlorine, that's also that structure. But furthermore, if I jump to the other side, if I take it away from this carbon, put that there, these are also equivalent to one another because of the symmetry in that molecule. Again, if I pick it and flip it over, I get the same thing. So there are 6 potential hydrogens that I could replace to get that compound there. So how we do this is number of hydrogens times the reactivity factor. So we said that there were 6 hydrogens. Which reactivity factor for chlorine am I going to use? Why 1? Because it's a primary carbon. Yep, so I'm going to use the reactivity factor for primary carbons, which would be 1. And so that would get me 6. So I got to do that for each one of these structures here. Okay? Take a second and see if you can't figure out how many hydrogens are going to go for these 2 products here. How many hydrogens could I replace to get to those 2 products? So sort of the way that I would do it is similar to what I did here, which was to draw out your potential products, and then you could figure out which carbon, how many hydrogens are on the particular carbon that you've substituted. Does that make sense? Correct. Before the chlorine was there, right? Because you're going to swap a hydrogen for that chlorine. That's how the reaction goes. So how many hydrogens could I swap to get to this same product is the question. All right, so actually this third one here is probably a little bit easier than the other one. How many hydrogens could I substitute out to get to this product here? All right, so it would be from this carbon here, which has 1, 2 hydrogens on it. All right, so replacing either one of those hydrogens would lead me to this product that I've circled here in purple. So that means 2 times the reactivity factor. Which reactivity factor am I going to use? 3.9. So that would be 7.8 maybe? That sounds right. Okay. And what about this last one? How many hydrogens could I swap out to get to this green product here? Nice, yeah, right? So I could replace either the hydrogens on this carbon to get there, or because of symmetry, the hydrogens on this carbon. So there are 4 potential candidates here. So now it's 4 times that reactivity factor. Which reactivity factor do I use? That 3.9 again, because it's a secondary carbon. So that gets me to, there we go. So then which one of these is the major product? 1, 2, or 3? 2, right? So this is my major product.
Will the reactivity numbers be given?
Yeah, I'll give you those. You don't have to memorize those. Okay, so now you can attempt this second one here.
is it by a carbon basis, or is it just like all of the degrees?
So you do look at each carbon, and you're gonna figure out whether it's. So you're talking about this first step, determining the more stable radical, or the next step?
Like there's like 3 1 degree ones. So would that be like 1 times like 9?
Yeah, absolutely.
And then like we would do like for the third degree we would like times 5.2 for the 1.
Yep. But it's all about like the fact that all 9 of those hydrogens are equivalent,
Okay.
right? If I replaced any one of them, I would get to the same product.
But we're not doing like the third degree versus the 1 degree.
You are in. This is how you're accounting for that by using 5.2 in your math for the third degree and a 1 in the math for your primary.
Okay.
That's kind of how you account for those preferences.
But do we do it times 3 for like the 1 degree because there's 3 of them, or do we do it times?
You do it times 9 in this particular case because replacing any one, a hydrogen on any one of those carbons would give you the same product, right? So to a first approximation, you can just go through and like draw all the potential things, right? I'm gonna put a chlorine here. I'm gonna put a chlorine here. I'm gonna put a chlorine here. But then I'm gonna see that all of these are equivalent.
Yeah, I was doing it wrong because I was doing it by like individual like carbons regardless of the molecule.
So the only thing that you're gonna miss that is that these 3 structures would be the same, right? So you'd be doing the math for 3 identical structures.
Yeah.
So hopefully you can see that these are my 2 potential products here. And I gotta do a little bit of math to figure out which one is going to be my major product. So you don't want to put them on, I see what you're doing kind of, but you don't want to put them on the same structure, right? Because this would be like this dichloro business. So you want to draw the 2 different structures, show me which one would be the major structure. You're doing your math and everything correctly.
But the answers are right
Besides
besides that.
that, I see how you did it, but like I want you to notice that like this is going to be a different molecule than what I said, right? Okay. The other thing is this is now bromine, not chlorine for these ones, which means that everything's the same except the numbers that you use in your math. What's that? Oh, okay, because there was just chlorine there, so I was.
Oh, yeah.
Okay, cool. Yep. Yep. All right, so for this first structure here, where I put the chlorine on the red carbon, I'm going to again have to do my math where I do the number of hydrogens times the reactivity factor. What am I going to use for number of hydrogens? 9, right? So again, you want to try to see that because of symmetry, yes, I could replace any 3 of those, but this molecule I can like rotate and it's the same thing, right? So also these, any one of these would give me that same structure. So this would be 9 times the reactivity factor, which would be 1 because it's a primary carbon, right? And then how many hydrogen, so for my orange structure here, does it look orange? Yeah. For my orange one here, how many hydrogens would I replace to get that structure? There's just one. There's just one chilling on that orange carbon there. So that's the only one that I could swap out to get that structure. So I'm going to do 1 times the reactivity factor. Which reactivity factor am I going to use? 5.2, because this is a tertiary carbon. Okay? So notice that actually the more stable, the major product rather, is going to be on that primary carbon. Even though it doesn't form the most stable radical, there are just so many more of those hydrogens, right? To some extent, it's a numbers game. So my major product is going to actually be substituted on that primary carbon. Okay, that's why we need to do the math to figure out our major product. All right, these last two examples are same sort of logic. The only difference is that you have bromine instead of chlorine, which means that you're going to use different reactivity factors. Right? So the numbers that you use in your math are going to be different for bromine. So for both of these, there was these practices on OWL for Chapter 2. The one was under the cyclohexane assignment, and the other one was under the reactions of alkanes assignment. On OWL, they were like relatively easy to kind of BS your way through, because it was like axial or equatorial, and you had 2 chances, right? So you could kind of just by default figure it out. Nonetheless, this would have been the correct way to do it, right? This would have been the long way that you should have been doing those problems, is to first figure, like fill in your diagram with the position, figure out which conformation is more stable, and that's how you determine whether that group was in the axial or equatorial position, okay? So you can practice on that OWL assignment. Do it right. Make sure you're getting it right the first time every time and not relying on your 2 chances, sort of guessing and checking and everything like that. But that's a way to do these problems. Same thing with these ones here. There were these problems that were like, how many, where does the radical go on the most stable intermediate? How many products are there potentially? And then which one's the major product, right? And again, kind of only had a few options so you could guess and check. But doing it the long way, doing it the correct way, you should be able to get those answers the first time around. Okay? There are some people that came in a little bit later, so you can fill in these nomenclature problems from the front page here. Again, I'm going to post this same sort of thing, but with different problems on there on Canvas afterwards, so that you can, again, just more practice, right? Yeah. All right? Break. We're going to do the same thing. So if you came in late, we're going to do the same thing for Chapter 3 on Friday, and we're going to take our exam on Monday instead. All right? So the exam's been postponed to Monday, so we can review Chapter 3 and then have the weekend to study all this business. Good. Yep. Yeah.
We're looking at this one. This both of them are.
Say it again.
They both are looking up.
Correct. They're both pointed at us.
Or us.
Yep.
So essentially, this is the.
That's perfect. Right. So you're gonna look at each carbon and you're gonna say which bond's on top, which bond's on bottom, and same thing here. So you were in the top bond on both positions.
So when I flip it, it's gonna be the opposite, and then this one's gonna be where they kind of like the same thing.
In this case, it's equivalent, but I will say that I think you just miscopied the problem, because there's another carbon sticking off of this one here. And then you'd be able to pick which one's which. But if I gave you this problem, you would just tell me that they're both equivalent, right? Because we got axial, equatorial, axial, equatorial, they're the same size.
Okay, and then one more time, if I'm not coming for the exam, I would just go to the testing center.
Correct, yep. So send me an email and we can arrange that.
Is it just gonna be the same? Oh, same.
Send me an email and I'll arrange it for you. Correct. All those would be different products there. So this is like worst case scenario where you got a bunch of different ones.
And then this one, so all the ones pointed up are not wedges.
All the ones pointed up are wedges, but so are the top ones in the equatorial position. So this one here is also a wedge, and that one's also a wedge. right? So it's not just the three that are pointed straight up. It's also, if we go here, the top bond in the equatorial position.
So it would look more like this, where
So this you have backwards. This we would want to have, this bond here is my wedge, and this one is my dash, right? Wedges are on top, dashes are on the bottom. That's regardless of whether you got a carbon where the wedge is in the equatorial position or the wedge is in the axial position,
okay.
right? So wedge is not necessarily always axial,
Right.
right? It has to do with which bond is on top. So in this case, this would be the wedge on top and the dash on bottom. The dash is actually the axial position.
So,
Okay? If you look on Canvas, I kind of made a little cheat sheet, and you're not going to have this for the exam, but just so you can kind of see, where I showed you, like here is a diagram where all the dashes and wedges are filled in. And again, if you just look at each carbon, you'll notice that the bond on top is always the wedge. The bond on bottom is always the dash.
and that doesn't mean it's always axial, though.
Correct, correct. They're two different things. We got to kind of keep them separate in our mind.
Right.
We can't always say wedge is axial. It's not that straightforward.
Okay.
Yep.
I have a quick question.
Yeah.
Did I get all my potential products, or am I missing one for this one?
There is one, and that is
It's that one?
yeah,
I
it's the
didn't know if
bromines
that
on
was
that.
the same as these two right here, so I did 9 hydrogens.
Yeah. So if you put it here, right? These carbons are the primary is right next door to the tertiary. Here, the primary is right next door to a secondary. So these aren't equivalent. If I have one more bond, it would be.
So then I just look for compare the carbons like this, since this is a third degree.
You definitely got your most stable radical right? But you are missing one more product, and this number shouldn't be 9, it would just be 6.
All right, thank you.
Yep.
I just have a quick question. Would it be okay if I add these on too?
That's fine, that's fine. Yep. I was just saying, in organic chemistry, we get a little lazy, and so you'll just see the organic product drawn.
Okay, I'm not sure if I did this one right.
So that's one of them, right? That's one of your potential products. The other one would be if the bromine is coming off of one of these 3 carbons here.
Oh, okay, so like, right there. and then
Oh,
I'm-
yeah. Okay, so you did your math. Yeah. This is the major. You're right. Okay.
Okay,
I didn't see your 2 potential over there. Yeah,
okay,
that's good.
thank you. I wanted to ask, so with these ones, one was, there's one on each, how would you know if it's actually?
Because the bigger group gets its say, right? So the bigger group wants to be in the equatorial position. So this is a little teeny tiny group, this one's big, so this one wins. It's gonna get to be in the equatorial position, even though this smaller group is in the axial position.
And then if they were the same size?
Then you would say they're equal.
Okay, thank you.
Yep. I don't have office hours today, no. I have class from 8 a.m. to 5:30 p.m. I do have office hours on Friday. Yeah, I mean, I'm sorry, I just don't have any time. You can send me an email and a screenshot, and I can try to do it that way, but I just don't have time to